AOPS number theory 12.45. The Fibonacci sequence is defined by f1 equals f2 equals 1 and fn plus 2 equals fn plus 1 plus fn. Find the remainder when f2006 is divided by 5. So since it's going to be divided by 5, we're going to use modulo 5. So we're just going to test all of them to find if there's like a repeating pattern between these, and then we can find the 2006 one. So f1 is equal to 1, which is congruent to 1 in modulo 5. f2 is congruent to 1 as well. f3 is equal to f1 plus f2, which is congruent to 1 plus 1, which is congruent to 2 in modulo 5. f4 is equal to f2 plus f3, which is congruent to 1 plus 2, which is congruent to 3 in modulo 5, and so on. So it's just equal to the previous two terms, and then we find what it's congruent to in modulo 5. And then when we do it all the way to the 28th one, then actually no, it goes up to the 20th one, and then it repeats after this. So it goes 1, 1, 2, 3, 0, all the way to 4, 1, 0, and then it repeats the whole thing again. So it repeats every 20 terms. So f2006 is congruent to f6, which is congruent to 3 in modulo 5, because f6 is congruent to 3. AOPS number theory 12.46. Find all prime numbers p for which p squared minus 1 is not a multiple of 24. So p is equal to 2k plus 1 for primes greater than 2, because all primes are odd except for 2, so it can be written as 2k plus 1. So that means p squared is 2k plus 1 squared, which is equal to 4k times k plus 1 plus 1. So since k or k plus 1 is even, because they're 1 apart, so one of them has to be even, that means 4k times k plus 1 plus 1 is congruent to 1 in modulo 8. Since k times k plus 1 is even, times 4 makes it a multiple of 8, and since there's a at plus 1, that means it's congruent to 1 in modulo 8. So that means the square is 1 more than a multiple of 8, since it's congruent to 1. So since all primes greater than 3 are congruent to 1 or 2 in modulo 3, and 1 squared is congruent to 2 squared, which is congruent to 1 modulo 3, that means the square is 1 more than a multiple of 3. Since it's not a primes greater than 3 is not a multiple of 2 or 3, so the LCM of 3 and 8, since it's modulo 8 and it's 3, is equal to 24. So 24 is divisible by p squared minus 1. So the only exceptions are when p is equal to 2 or p is equal to 3, because that's the only way this wouldn't work. AOPS number theory 12.47. Prove that among any 51 integers, there are 2 whose squares have the same remainder when divided by 100. So the pigeonhole principle tells us that among any 51 integers, there are 2 with the same modulo 50 residue. So the pigeonhole principle is basically like if there's 50 different residues or 49 different residues in modulo 50, then and there are 51 integers, then there must be 2 with the same modulo 50 residue, because there are more integers than the number of residues. So these integers can be 50n plus r. So 50n plus r squared is, since it asks for the square, is congruent, if you do all the calculations, it's congruent to r squared in modulo 100. So the value of n doesn't affect the modulo 100 residue. So there must be at least two different numbers whose squares have the same remainder when divided by 100.